All right, let's take a look at Chapter 5, Lesson 2. We'll probably split this into a couple of videos. They get a little bit long. So this first part, we're actually going to address everything that we see on here, what Riemann sums, the idea of a definite integral, what that is, how to use calculator to approximate the value of a definite integral, and what is meant by integrability. Second semester is referred to as integral calculus. Its heart is about integrals, and definite integrals certainly a part of that, in the way that first semester was differential calculus and focus on derivatives. Okay, so our picture in first semester, everything was about slope, and the picture that we're going to try to rely on here is area, although it's not quite as exact that way in this semester. All right, so what is a Riemann sum? Okay. The definition here, we'll let f be any function defined on a closed interval from a to b for any partition p of that closed interval. Let the numbers c sub k be chosen arbitrarily in the subinterval from x sub k minus 1 to x sub k. So we've got some function on a to b. We're good with that. What is a partition? Partition of ab is a way of breaking the interval from a to b up into subintervals. Okay, and we mark the beginnings and ends of subintervals with different x's that have their own subscripts to say where they are along the way. So the very first one that corresponds to where a is x sub 0, x sub n is where b is, and we've got x sub 1 and 2 and 3 and 4 and 5 on everywhere else in between. Okay, so that's the picture that we have. C sub k is taken from one of those subintervals. So C sub 2 is from the subinterval that goes from x sub 1 to x sub 2. Okay, so that's just the way that that it defined it there. Okay, so here's the theorem. With all that set up, it says if there exists a number I such that the limit as the absolute value of p goes to 0 of the sum from k equals 1 to n of f of c sub k times delta x sub k, okay, equals that number. Okay, no matter how the partition is chosen and how the c sub k's are chosen within each subinterval, then we say that the function is integrable on the interval from a to b, and that I is the definite integral. So the limit has to exist. If the limit exists, it has a definite integral. If the limit does not exist, okay, then we don't have the definite integral, and the function is not integrable, at least not on the interval from a to b. So let's take a look at what we've got here. Okay, so the things we're familiar with, f of c sub k, this is the height of our rectangles. Okay, what we've done with the rectangular approximation methods is one case of a Riemann sum, where we've made some choices very specifically and defined them very well. So the value of the function using the input from the interval to determine the height of the rectangle. And then we have the x of x sub k, delta x sub k, which is the width of that rectangle. So it's still about adding up areas of rectangles. In fact, that's what this symbol here means. This is the Greek letter capital sigma, and in math it means that you are summing, you are adding some things up, and we're adding in things together. And what are the things that we're adding together? Well, we're adding these in rectangles that have been made on here. Now the calculus comes in right here where we do this limit, okay? And the absolute value of p going to 0 is telling us that the magnitude of the largest segment in the partition. Okay, so if we look at all the subintervals that were created, and it's saying the longest subinterval, if you make so many breaks in this thing that the longest subinterval is going towards 0 as its length, okay, and you approach this particular number. Okay, well that's a very calculus feeling to us, that we've got to get those things down so these rectangles aren't so jagged looking. Okay, and that's what's being accomplished by that limit of the magnitude of p going to 0, is it's making so many rectangles that it's not so jagged looking, and it's starting to look smooth. Okay. All right, so where that's showing in the picture here, we've got, here is, went made too far on that one. Okay, here is x0 to x1, here is x1 to x2, here is x2 to probably what would have been x3, but they start to generalize here in the middle. They've identified that in that first one, from x0 to x1, the C1 they chose was this point right here. Plug that into the function, we get this as an output, and it says use that as the height, use x1 to x0 to x1 as the width, and calculate that area. Okay. C2 has been marked right here. If we put that in, it looks like it was kind of like the midpoint. The first one looked like it was the left-hand side, but the Riemann sum was not specific about where you had to choose it. It could be anything in there. Maybe chose this was a midpoint, or because it made the lowest point, the biggest rectangle that made sense in that area, and find that area. Okay, so that's the idea of the picture there. We can't picture the limit as magnitude of the partition goes to 0, because that would require, if we think about it, more rectangles than we could possibly draw, because we're taking the jagged nature out of it. In this picture, things are still very jagged. Okay, so let's refine this a little bit, and let's add the stipulation that our function is continuous. And it turns out that if the function is continuous, then the definite integral will exist, guaranteed on the closed interval from a to b. Okay, and so we can change the way that we define it a little bit. It says let f be a continuous function on the closed interval from a to b, and we're going to let a to b be partitioned into n subintervals of equal length. So that's what we did in our rectangular approximation methods. We made them all the same, and that's fine. There's no problem there. That fits in with what Riemann said we could do. And then the definite integral of f over the interval from a to b will be given by this formula. The limit as n goes to infinity of the sum from k equals 1 to n of f of c sub k times delta x. Now, most of this looks exactly like what we had before. We still have the f of c sub k. This is the height of the rectangle. Our c sub k we could define as being the left or the right or the middle, however we want to do that. The delta x is still the width, but I don't need a subscript on it now because I made them all the same size. Okay. I notice the summation is still there. We're still adding up the areas of the rectangles, but my limit takes on a little bit different look here. It's not talking specifically about the partition, but it's saying n is the number of rectangles that we're going to make. And so it says as you go toward making an infinite number of rectangles. Well, if you make an infinite number of rectangles, then the biggest one on the bottom is definitely going to 0. Certainly ours would be going to 0 here because we've got a fixed number divided by a number that's going to infinity. This b minus a over n, as n goes to infinity, is definitely heading towards 0. So that satisfies the limit of the magnitude of the partition going towards 0. We have followed along here. We've made a specific choice about our width of the intervals that we've got in there, and we're still arbitrarily choosing a c value from any point. So that fits all of our definition of that, and this should then give us the definite integral I. Okay, so what we were doing fits into the theory, and so now we're going to try to translate that into something that looks a little bit more calculus-y. Okay, this looks like, again, the limit chapter before we got to the derivatives. Okay, so Leibniz and his little French friends, they were the ones that came up with most of the notation that we use. And if they thought back to what they did in the differential calculus part of this, they took this idea of slope of a change in y over change in x, and the capital letter delta in the Greek has always stood for change in mathematics. anyway. And so they said, okay, we'll take this, which represents our secant lines, our slopes through 2 points, and through the evaluations of limits, this we're going to change into a dy dx, the delta x, because we squeezed down to a single point, and now these both technically are 0, but not quite, because we're just doing the limit as we get close to it. And so to signify that, they changed from the Greek letters to our alphabet along the way. And so to be consistent with that, they're going to do the same thing in integral calculus. And the thing that they have to change is this sigma. There's our Greek letter, capital sigma, which is normally translated as an S. Okay? Well, S, if you've tried to work with variables of S, you know you run into problems. They become 5. They become all kinds of issues with that. So they decided, well, what if we stretched it out a little bit? We'll stretch it out a little bit more and do something that looks like that. So this is a skinny, stretched out S. That is what that symbol is. Okay? For us, it stands for the integral. This is the integral symbol. It came from being an S to be consistent with the change from the Greek to our alphabet. So what is the rest of what's going on here? No big surprises over here. We have a height, again, determined by the value of the function, and it's multiplied by a width. Okay. So it's height times width. It's still an area of a rectangle, the summation symbol. We're adding up the areas of the rectangles, okay, just like we did before. Just like it did in differential calculus, the delta x becomes a dx. There's going to be lots of those kinds of connections that we're going to see. And the c sub k became an x. And the reason it can do that is because we're letting that limit as n goes to infinity. So we're making an infinite number of rectangles. And if you do that, then the difference between the left side and the right side and the middle and anywhere else on there is becoming less and less. And in fact, at the point that you would have squeezed the width down to 0, then there really is only one choice. The left and the right and the middle and everything else is the same value, and so we can just call that x. Okay. This notation has the added benefit that we can put in the information about the closed interval. So we have this is the left-hand side of the interval, and this is the right-hand side of the interval. And so this is our new notation that we are transferring into as we study integral calculus. Okay. So, as an example, the interval, closed interval from -2 to 4 is partitioned into n subintervals of equal length equal to 6 over n, because the width of the interval is 6, and we're going to make n of those, okay? And we're going to make them all the same size. M sub k is the midpoint of the kth subinterval, so they've chosen the c sub k to be the midpoint, okay? And they want us to express this limit as n goes to infinity of the sum from k equals 1 to n of 3m sub k squared minus 2m sub k plus 5, all times delta x as an integral, okay? Well, the summation symbol becomes our integral symbol. We are starting at -2 on the left, ending at 4 on the right. Okay? Because the n is going to infinity, the m sub k is becoming a single number, so that becomes a 3x squared minus 2x plus 5. That is the height of every little skinny rectangle, which has a skinny little width of dx, and this is what that looks like as a definite integral. So the next question is, well, if this is supposed to be equal to some number, how do we get the number out of that? Okay, and that's what most of the rest of this semester is about. Okay, other than the application kinds of chapters, but we're going to look at how to get the number out of this. And unfortunately, I can't make the same promise I did in the first semester. First semester, I said you'd be able to do the derivative of anything by the end. We're not always going to be able to do this. We're always going to be able to come up with approximations. We're not always necessarily going to be able to come up with exact answers. Okay? It's a more complicated process. So we're going to spend a chapter looking at how to do the approximations so that we get good at doing the approximations for the ones that we can't figure out how to do exact answers for, and then we'll start looking at ways that we might be able to come up with exact answers for the ones that are actually possible. Okay? So the first step in the approximation is technology. So we're going to take a look at how you can do this on the graphing calculator. And then once we've looked at it on the graphing calculator, then we're also going to take a look at how you can come up with these approximations in Desmos. And for some of them, these fairly simple problems that we have been looking at, and we're going to continue to look at this particular example of the 3x squared minus 2x plus 5 on the interval from -2 to 4. We're going to see if we can get the calculators to give us numbers for those. So I have a TI-83 and a TI-84 here because they behave slightly differently. I got to get these screens off of here. Okay, so first place we're going to go is to the home screen. The place that we find this is in the math menu. Okay, and if you scroll down in the math menu at option number 9, you see this thing that says FN int. Okay, that is the numerical integral of that. That's what we're trying to do. We get a very different look on the 83 than we do on the 84. The 84, it's pretty obvious what we should be doing. The -2 goes there, the 4 goes there, the 3x squared minus 2x plus 5 goes there, and that's supposed to be with a dx. Okay. On this side, we have to put the function in first, so we'll put in the 3x squared minus 2x plus 5, and then we need a comma, which is right above the 7, and we're going to tell it the variable is x. That's what normally would go after the dx, and then the left-hand side is -2, and the right-hand side is 4. Okay. I usually read this as the numerical integral of 3x squared minus 2x plus 5 as x goes from -2 to 4. Okay. I'll hit enter on these simultaneously. Gives me an approximation of 90. That's probably the exact answer. Okay, this does a pretty good job, and we'll figure out by the end of this chapter which approximation method the calculator actually uses to come up with these. Okay, that's one way to do it with the calculator. Another way to do it with the calculator is to first of all graph the function. So I've got the 3x squared minus 2x plus 5 entered in both of these, and I will graph those. And then if I go to second trace to get into the calculate menu, I see that option number 7 has that definite integral, or that integral symbol on it. So I am going to choose that option on both of these, and it's asking what is the lower limit. Well, I want to go -2 to 4, so I'm going to put the -2 in and hit enter. And then I want to go to 4. That's the upper when it asks it. And it does this little shading business. The 84 Silver's got a faster processor, did it? So it's like shading in all of the little rectangles that it did, and comes up with an answer there of 90 as an approximation as well. Okay? It will not always nail it exactly right. Okay? It tends to have problems when the function is very, very steep. Then it tends to get off a little bit. Okay? But most of the time it does a pretty good job. Okay? So let's pump into Desmos here. If we're going to do this in Desmos, I've already entered the 3x squared minus 2x plus 5 as a function here. It's not going to do the cool graph business over here with the shading, but in my keypad, and under the functions, if I go into the miscellaneous, then I can find my integral sign there. And I can see pretty much what it is that it wants me to do there. All right, so we can do it that way, or if you don't want to pull up all that menu, if you just type INT, it does the same thing. And so we're going to go -2, tab, 4, tab. I already entered the function in here, up here, and gave it a name. So I will just do f of x, d, and as soon as I put the x in there, it gives me a 90 as the approximate answer for that. Okay, so that's how I can come up with approximations of definite integrals using technology. So that's a nice thing to have. And we will explore a little bit more in this lesson on another video, but I'm going to cut this one off right here.